This one here, what you're going to have to do, this is very different from the other ones, right? Because we have addition and subtraction going on. You're going to have to simplify that radical. Let's take it off to the side. Let's look at the square root of 75. Set up our two radicals, perfect squares, whatever's left. What's the largest perfect square that goes into 75? Okay. And you know money. It goes in 3 times. So now we take the square root of 25 and we get... Okay, let's go back to that now. We have 10 minus the square root of 75, which we just said is 5 square root of 3. Over 5. See if you can cancel without factoring out the GCF. Do we have a common factor in every term? We have a factor of 5 in every single term, right? 5 goes into this once. 5 goes into this once. 5 goes into this twice. We're left with 2 minus just the square root of 3. Do we have to put over 1? No. Are we wrong if we do? No. It doesn't look very pretty though, does it? Now we're on the new note sheet. Recall, in algebra, we may combine like terms when adding and subtracting by adding the coefficients and keeping the variables, right? They have to be like terms. So looking at that example, we have 2x minus 3y plus 3x. Do we have any like terms there? We can only combine our like terms. We can combine the 2x and the 3x. We cannot combine them with that negative 3y. So we get, how about 5x minus 3y? Now, remember, like terms contain exactly the same variables, right? With exactly the same exponents. It wasn't enough to have them both be x's. They had to have the same power. So looking down here, well, every term has x's and y's, right? But this one has xy to the first power. They're both to the first power. So I can't combine that with this. I can't combine that with this, but I can combine it with this. So I have 2 of these plus 7 of these. I get 9 of them. Okay, I'm going to slash... No, because we're adding. We use that, right? Are there any other like terms? No, these are not alike, so we can't combine them. So we could just say plus 3x squared y minus 9x. Square roots are like square root if each square root has exactly the same, what do you think? Well, radicand. More than variable. It has to have the same exact radicand. And I am going to tell you that later we're going to find it also has to have the same index. So in other words, cube roots and square roots are not going to be like terms, even if they have the same radicand. They have to be the same in both respects. So looking at the first example, I have 2 of these, plus 3 of those, and then 3 of these. So which ones can we combine? Yeah. Now first and last, these are like terms because they have exactly the same radical. You know, they're both square roots and the same radicand. Now think of this like you do algebra. 2 of these plus 3 of these is? So we have 5 of those now. Can't do anything more with this. We're done. Okay, see if you can do the next one. Next one, they're like radicals, aren't we? So we can just add them. We have 5 of these plus 4 of these. We have... Okay, now what's your question on this one?
We assume that there is a 1 outside of the
Yes, just like an x. If you had just an x, it's like a 1x, right? So we have 12 of these minus 9 of them plus 1 of them. We have 4 of them. Last one. 2 square root of 3 plus 3 square root of 2 minus 5 square root of 3. Which one? Negative 3 what? Okay, so you want negative 3 square root of 3? Then what?
Plus 3 square root of 3.
That's correct. So we combined the 2 like terms, and this one was not a like term because the radicand was different. They're all square roots, but these had a radicand of 3, and this had a radicand of 2. Does anyone have any questions? Okay. Now we have to consider everything. Like terms must have. Now when we look at variables, they have to have what? They have to have the same variables, right? Oh, don't do this, because it's a table. All right. I'm going to put it up here. It should be variables in that line. Let's see. Okay. With exactly the same what? Exponents. Remember, our variables had to have the same exponents. I guess I have to do away with tables. It doesn't like when we try to write in a table. Radicals have to have exactly the same radicand. Oh, God. Okay? With exactly the same index, okay? Give it up. That little, where it's a square root, and I said when we get to cube roots, there's going to be a number in there. So right now, let's look at it on the board. A 2 is implied here. We didn't write anything, but that's square root. If it were a cube root, we'd have to put it. That value is the index. So we're dealing with square roots. Our index is a 2. We don't even have to worry about that right now, but later you will. So I'm just kind of getting you set up for it. Okay, so looking at this first example, which thank God is not in the table, we have 5 square root of x. Do we have anything else that looks like which one?
7 or 2 if altogether it's inside.
Okay, these two are like terms. This is not because the x is not under the radical. That matters, right? The radicands are different. So we can combine these two, so we get 7 square root of x. Okay, and now these two, are they like terms? When we look at the radicands, they are the same, right? They're both 6. They're both square roots. Now what about our variables? Well, they both have x to the first power. They are like terms. So really, I have 4 of these, right, minus 3 of these. So how many of those do I have? So I want plus 1 of those. Am I wrong if I put a 1 out front? No. Do I have to? No. I don't, because I know as you move forward in math, no one's going to, and you won't know what it means then. Okay, so let's see if we can do some of these. Now, here's the thing. At the top of the page, it says, often we have to... Do these look like radicals right here? No, but they are. Well, we can't see it because we have to simplify. In order to see that they are like radicals. All right, now these you can do in place. We're going to simplify first, both. So let's look at the square root of 12. 2 radicals, perfect squares, whatever's left. What the largest perfect square that goes into 12 is? And we're left with 3. I would suggest doing one at a time. Because if you're anything like me, my handwriting's awful, and then I could get mixed up later. I know what I just wrote. So what's the square root of 4? So we get 2 square root of 3. Now I go to the next term.
Wait, why did you get rid of the plus sign?
I didn't. I'm going in now. I'm doing it a piece at a time because I'm just afraid later I can't read my writing. These are things people with bad handwriting have to do. Square root of 27. We want to find the largest perfect square that goes into 27. 9. Okay, 9 goes in 3 times. Please write out every step. When you try to jump steps, you get in trouble. Now, this is a perfect square. We created that. What's the square root of 9?
3.
So we have 3 square root of 3. Are these like terms? Yeah, they have like radicals, right? Same radicand, same index. So we have 2 of these plus 3 of these. We have addition on these is not like fractions. Addition on these is actually kind of fun. It's actually, to me, one of the easier sections. Okay, let's do it again. We're going to set up 2 radicals for the 20. Perfect square is whatever's left. What's the biggest perfect square? It goes at 20. And we're left with 5. Let's simplify it. The square root of 4 is? So we set this up so that this will be a perfect square radical, and we can take the square root. This is not, and we just keep it. Okay, plus, and now we're going to put 2 radicals. What's the largest perfect square that goes into 45? 9 times 5. Okay, what's the square root of 9? And that's supposed to be a 5 under there, but it keeps dropping my hat. Are they like terms now? 2 of these plus 3 of these is 5 of these. What do I do when I get on an exam if I either get really nervous on exams and forget everything I know, or I simply don't know my perfect squares like Mrs. Davis told me to? What do I do when I get on an exam? I sit there with my scrap paper and my calculator and I make a darn list. So I can keep looking at it, right? There's no reason you can't do that. It's really good if you know your perfect squares. That's what I really want. But I also know some people lose their head in the exam, right?